Uh, Good evening, one and all. Today we have parallel technical session 22nd in Hall B. We have total 5 presentations. After the state of the art practice lecture delivered by Professor Brady R. Crox from Utah State University. And for this technical session, we have chair and then co-chair. And it is my pleasure to introduce for this technical session our chair, Dr. Vijayendra. Dr. Vijayendra is a senior professor in Bengaluru Institute of Technology. He obtained his BE degree in civil engineering and ME degree in geotechnical engineering from University of Visvesvaraya College of Engineering (UVCE) under Bengaluru University. He completed PhD from National Institute of Technology, Surathkal, and is a member of several professional bodies, including Indian Geotechnical Society and the Indian Society for Earthquake Technology. He is currently teaching at the Department of Civil Engineering at his own parent institution. As I found him, he is a very active researcher and a very interesting personality. He is an excellent teacher and he is having research experience for nearly 2.5 decades. And his areas of expertise involve soil dynamics and earthquake engineering, ground response studies, and seismic hazard analysis. So on behalf of the organizing committee and on my personal behalf, I invite Dr. Vijayendra uh, to chair the session for this event. Vijayendra, I welcome you to chair the session.
Thank you, Professor Govindraju, for that kind words and nice introduction. We have this session on the third day.
One second. I have to just a minute. I have to introduce co-chair. I will invite. Yeah. Now it is my pleasure to invite our co-chair, Dr. Chandra Bogi Reddy. I would like to introduce him to the delegates who are present here. Dr. Chandra Bogi Reddy is assistant professor in the Department of Civil Engineering of Geotechnical Engineering Division at Vardhaman College of Engineering, Hyderabad. In the year 2019, his PhD degree was awarded, titled under the thesis Rapid Assessment of Compressibility Behavior of Clay Soil from Experimental and Finite Element Simulations from Civil Engineering Department, SVNIT, Surat. He received 2 Best Paper Awards in the National Conference and also he delivered 10 guest lectures in various national level seminars. He is associate member of I.I.Sc, SM, ICE, MI, and then life member of Indian Society of Earthquake Technology, life member of ISRMTT, and fellow of FSIESRP. So with this brief introduction, I invite Dr. Chandra Bogireddy on behalf of the organizing committee to chair this session.
Thank you so much,
Chandra Bogireddy, please, I welcome you to chair this session.
Thank you.
Before start of the session, it's just like a small information to chair and then co-chair. Organizing committee has decided to identify the best paper presenter award only from the students stream, and then out of the presentations, the chair and then co-chair are requested to finalize one name and kindly forward it to the organizing committee so that the best paper awardee will get a prize, okay, in the valedictory function. So now I will hand over the platform to the chair and co-chair.
Thank you, Professor Govindraju, for that nice introduction. Also, I thank my co-chair, my colleague, and the secretary of the event, Professor Jekka, for giving me this opportunity. And not the least, I welcome Professor Bardi or Cox to deliver the state-of-the-art lecture of the session. And also welcome all the presenters today. We have 5 papers. To start with, let me formally introduce Professor Cox. Professor Cox is a professor in the Department of Civil and Environmental Engineering Department at the Utah State University. Prior to joining USU, he served on the faculty of University of Texas for 8 years and the University of Arkansas for 6 years. Dr. Cox specializes in geotechnical engineering with emphasis on issues related to seismic design and in situ characterization of major construction projects. His research efforts combines the experimental field investigation with computational analysis, particularly for high performance computing with subsurface imaging process. He has led teams deployed to collect the seismic site characterization data at the ground motion recording stations, soil liquefaction sites, and structural failures following the significant earthquakes in the US and around the world, which includes Japan, New Zealand, Peru, etc. He has also participated in numerous dynamic site characterization projects for the seismic design of critical facilities like nuclear power plants and others in the US and abroad. Dr. Cox is a recipient of prestigious Faculty Early Career Development Award from the US National Science Foundation and the Presidential Early Career Award for Scientists and Engineers, which he received in a ceremony at the White House from President Barack Obama. He has authored more than 100 peer-reviewed publications and has taught 8 different courses at the undergraduate and graduate levels at 3 different universities. On the personal note, he grew up as a son of a tough and hardworking coal miner in Helper, Utah. His personal life is influenced by 5 important women, his wife and his 4 daughters. He loves all outdoor activities and currently spends quite a bit of time training for endurance sports, having recently completed an Ironman triathlon and 50-mile ultra marathon. So he is sportive, is researcher, active researcher, and a well-known teacher also. And I welcome Professor Bardi Cox for delivering his lecture, state-of-the-art lecture on H/V, geostatistical approach to account for spatial variability in 1D seismic site characterization. I request Professor Bardi Cox to deliver his lecture now. Thank you.
Thank you for that great introduction. I really appreciate it. It was perhaps too long for everyone to hear, but hopefully it wasn't too painful. I'm going to.
It was interesting.
Good. Thank you very much. Well, it's very early in the morning here in Utah, where I live, about 4:30 a.m. And I know it's in the afternoon where you are. I wish that I could have joined you in person, but hopefully the presentation will still be of value to everyone. Can everyone see my screen before I continue my presentation?
Yes, it is clear.
Good.
Clear.
So I would like to quickly acknowledge my current PhD student, Mohammed Halal, who is still at the University of Texas. All of my slides have this banner for the University of Texas because the work I did was at the University of Texas, and my PhD student is still there. And I am currently at Utah State University. I moved universities about almost a year ago, let's say. So first of all, when we talk about site response, we're studying the amplification and the changes in frequency content of earthquake ground motions as they propagate from bedrock or some reference subsurface condition up to the ground surface. And in order to understand site response better, we found that it's very useful to use borehole array sites. And there's numerous borehole array sites around the world. I've highlighted some of the borehole array sites in California, in the US, and also in Japan. And I'm not sure, you may also have a number of borehole array sites in India as well. But these are wonderful tools where we're able to record seismic ground motions, both at depth and at the surface. And then we can, from those recorded ground motions, we can do predictions of site response and see how well our predictions match the recordings. One of the issues that we found, though, as more and more researchers have studied earthquake recordings from borehole array sites, is that we generally are probably not as good as we would like to be in terms of simulating or modeling site response. And here, this figure presents a synthesis from 5 major research studies, all using borehole array site data, and totaling 662 sites around the world. And basically, depending on the study that you look at, there have been approximately 30 to 80% of the sites studied that are poorly modeled using 1D ground response analysis. And so you can see, for example, this large study published in 2019 by Marco Pils and Fabrice Coton, of the sites that they studied, where they studied more than 200, only 45% of the sites were poorly modeled. And if you look at Thompson et al. From 2012, 82% of the sites they studied were poorly modeled using 1D ground response analyses. So results vary depending on many things, but in general, I think it's fair to say that we are not as good at doing site response as we think. And so these studies collectively challenge the wide applicability of 1D ground response analyses. And while 3D ground response analyses could be used, generally we lack site-specific 3D subsurface models, and also the 3D GRAs are computationally expensive. And these two challenges really prohibit us from performing 3D ground response analyses, at least on a wide scale. So the question then becomes, can we still use 1D ground response analyses, but improve their performance by accounting somehow for spatial variability on a site-specific approach? And today I'm going to talk about a new framework that we call the H/V geostatistical approach. And we can use this H/V geostatistical approach to develop site-specific 3D VS models. We call them pseudo 3D VS models, and I'll show you why later. But it's really a rapid technique that can be performed very cost effectively, that will allow us to incorporate spatial variability on a site-specific scale to be used in ground response studies. It requires only a single shear wave velocity profile. You can use more than one, but it requires only a single VS profile. That VS profile can be measured in a borehole, or it could be developed through surface wave methods. It relies heavily on spatially distributed H/V measurements, and I'll talk about those in just a minute. And then it integrates geostatistical modeling tools to develop the 3D subsurface model. So in terms of where I'm going in this presentation, I'll first discuss very briefly what H/V measurements are. I'll then talk about the geostatistical approach we use for developing the subsurface models. And then I'll show applications at 2 US borehole array sites, the Treasure Island downhole array and the Delaney Park downhole array. And then we'll talk about the implementation of the 3D subsurface model in ground response analyses at both of those borehole array sites. And then we'll compare this new approach, the H/V geostatistical approach, with standard methods that people use to account for VS variability, such as shear wave velocity randomization, and then I'll provide some concluding remarks. So first of all, an overview of H over V measurements. We use background noise, or microtremors, as called by some, to infer properties of the subsurface. And how we do that is we put a sensor on the ground. That needs to be a 3-component sensor, preferably something like a broadband seismometer. That's typically what I use. You record 3 components of ambient vibration. Once that ambient vibration is recorded, typically for 30 minutes, sometimes a couple of hours, we process the north, south, and east, west horizontal components. We take their Fourier amplitude spectrum, and we divide the Fourier amplitude spectrum of the horizontal components by the Fourier amplitude spectrum of the vertical component. And when we do that, if the site has a strong impedance contrast, and if the records are of sufficient quality, we often see that the H over V spectrum, which is shown down here, often has a peak in it, and sometimes more than one peak. But the lowest frequency peak, we call that F0, or the fundamental frequency. And I have the subscript H over V to make sure that we understand this is an estimate of the fundamental frequency from H over V testing. And that fundamental frequency is related to, using this well-known quarter wavelength equation, to the average shear wave velocity over the depth of the soil on top of bedrock, divided by 4 times the thickness of the soil layer. And so this is a rough approximation, this quarter wavelength equation, but it helps us understand how the stiffness, represented by Vs, and the thickness of the soil, represented by H, control the fundamental frequency of the site, which is a really key parameter for site response. So the H over V geostatistical technique is dependent on performing a number of spatially distributed H over V measurements, and then we extract F0 from those H over V measurements at every single location around a site. And in this case, don't worry too much about the exact size of the area and the number of measurements. It's just a schematic. But suffice it to say, we need to perform these measurements in some locations around our site. And then we're going to use geostatistical kriging in order to change those irregularly sampled H over V measurement locations into a uniform map on a grid. And these grid cells could be every 50 meters, every 100 meters, every 10 meters. It depends on the site, the size, as well as the density of the measurement locations. But we then end up with a uniform map showing the fundamental site period variation across our construction site. We have a measured shear wave velocity profile somewhere on the site. In this case, we happen to show it right in the middle, but it doesn't have to be that way. And again, you could use more than one measured VS profile, but in this example, we're just showing one. This happens to be a shear wave velocity profile that was measured using PS suspension logging. We then need to somehow modify this shear wave velocity profile and scale it so that it's, when we move this shear wave velocity profile from, say, here in the middle over here to somewhere in the blue where the F0 is higher, that this shear wave velocity profile will give us the correct fundamental site frequency. So we're going to have to modify this shear wave velocity profile numerous times. There's multiple ways to do that. You could simply scale the VS. You could increase or decrease the shear wave velocity profile to change the fundamental site period, and then develop a scaling factor. You could also change the thickness instead of changing the stiffness. So you could raise or lower this impedance contrast boundary, and that would change the fundamental site frequency implied by the shear wave velocity profile. You could change both the shear wave velocity and the thickness of the soil, and that would also change the fundamental site frequency. In fact, there are many, many options, and it's really an ill-posed and non-unique process. So we don't know exactly what to do without making site-specific measurements, but to make site-specific measurements at every location is not cost-effective. So what we decided to do in this work is not just scale VS, because that could yield unrealistic shear wave velocities. We decided that, generally speaking, the thickness of the soil deposits are the major contributor to the fundamental site frequency. And so we chose predominantly to scale the thickness of the soil deposits in order to get a shear wave velocity profile that would match the fundamental site frequencies from our kriging. So with that being said, we're going back to this general schematic. We take a measurement of the fundamental site frequency near the shear wave velocity profile of interest, and we develop these scaling factors. The scaling factors are simply the ratio between F naught at the location of the shear wave velocity profile and F naught everywhere else in this grid of this map. And those, then we can get a scaling factor for every cell, and we apply that scaling factor uniformly to every single layer or every single geologic formation in the shear wave velocity profile, so that we scale the thickness up or down in order to match the fundamental site frequency. And when we apply those scaling factors, for example, we can take that single measured shear wave velocity profile and obtain a bunch of different shear wave velocity profiles. In this case, they're color coded to the same colors on our H over V map. So we can visualize the variation of shear wave velocity across our site in 1D, but we can also create 2-dimensional or 3-dimensional subsurface models using this approach. And the reason we call it a pseudo 3D model is because we've estimated the shear wave velocity in 3 dimensions rather than measured it in 3 dimensions. So we're going to apply this method at several US borehole array sites. The first one being the Treasure Island downhole array, which is here in Northern California near San Francisco. And the second one being the Delaney Park downhole array, which is in Anchorage, Alaska. I'll focus predominantly on Treasure Island. And so Treasure Island is in San Francisco Bay, and it's this large island right here. It's actually a man-made island. It was created through hydraulic fill means to host the World Fair, and I believe like 1912 or something like that. It's right next to a rock outcrop called Yerba Buena Island. And so often this is a nice case study for seismic site response, and some of you may have studied it in a course in the past. But this is the rock outcrop, Yerba Buena Island. This is the Oakland Bay Bridge here that goes from Oakland, California over to San Francisco, California. And then this is Treasure Island here in the background. So what we did is we deployed approximately 100 H over V station measurement locations on Treasure Island. It took us only a matter of 2 days. We also performed surface wave testing, so some of the H over V measurements are clustered in groups for large surface wave arrays. But from those 100 H over V measurements, you can see that a lot of the F naught values on this site on Treasure Island are fairly uniform, varying somewhere around 0.8 hertz, maybe to 0.6 hertz. But as you get close to Yerba Buena Island, which is over here, obviously the fundamental site frequency increases and the rock gets, or the response is stiffer because the soil deposits are thinning as you get close to the rock outcrop. So we took those 100 H over V measurements, which are spread out over 1.5 kilometers in this direction, and about 0.8 kilometers or so, 800 meters in this direction. And we used geostatistical kriging to develop a uniform map of site period on a 50-meter cell, grid cell spacing. We then took this shear wave velocity profile, which was measured using PS suspension logging, and it is located right at the this borehole array where we have uphole and downhole accelerometers. And we scaled those 1D VS profiles to match F naught at every single cell. And obviously we can develop two-dimensional or three-dimensional subsurface models using this technique. In the two-dimensional cross-section, I'll point out here, every one of these white markers represents the location of an accelerometer in the Treasure Island borehole array. So once we have this 3D model, if we want to incorporate it into 1D ground response analyses, we're not going to use the complete three-dimensional model. We're going to use these 1D VS profiles. And what we'll do is we'll perform site response for every single one of these one-dimensional VS profiles. And then we'll combine the transfer functions and take something like a log normal median of the individual 1D ground response analyses. And we would call that a spatially aggregated approach to developing a median estimate of the site response. And the cool thing about this, the 3D, pseudo 3D VS model is that we can investigate incorporating different spatial areas. And we can study the site response at these borehole array sites and decide how big of an area do we need to incorporate in order to best match the recorded ground motions. And so in order to study our ability to predict accurately, we're going to use the empirical transfer function, which is a measure of the recorded ground motions at the site. So we'll simply take the deepest rock accelerometer ground motion, and we'll divide the surface output accelerometer by the rock accelerometer, and we'll develop what we call the empirical or experimental transfer function, the ETF. So this is a measurement of the actual recorded ground motion at the site. And then we can use the shear wave velocity profile to do a prediction of the theoretical transfer function. And this is a simple closed form solution for linear viscoelastic site response. And we're going to be using only small strain ground motions so that we don't have to worry about modeling the soil nonlinearity. So here you can see that the theoretical transfer function matches fairly well with the empirical transfer function in terms of the locations of the peaks, but not so well in terms of the amplitude, particularly at the fundamental mode of site response. We're going to judge in this study the goodness of fit between the empirical transfer function and the theoretical transfer function using two metrics. The first is the Pearson correlation coefficient, which was proposed by Thompson et al. In 2012, which predominantly judges the alignment of the peaks in the transfer functions. And that's called the R coefficient right here, the Pearson correlation coefficient. We're also going to use a metric that we developed called a transfer function misfit, which judges a little bit better the differences in amplitude between the empirical and the theoretical transfer function. And so you'll see me in the next slides compare both R values and MTF, or transfer function misfit values. So at Treasure Island, we used approximately 50 small strain ground motions to develop the empirical transfer function and its log normal median. And that's shown here in black. So the black lines are the median and the plus and minus 1 sigma on the recorded ground motions at Treasure Island, small strain. And then the green line is the theoretical transfer function from the PS suspension log. And you can see that it actually does quite well at matching the peaks, but in particularly the fundamental frequency, we're underestimating the width and we're overestimating the amplitude of the site response. So that Pearson correlation coefficient, that R value for the VS profile that was measured in the borehole, is about almost 0.65. Now, when Thompson said that an R value greater than 0.6 means that you're generally modeling the site response fairly well. So Treasure Island is a pretty well-behaved borehole array site. There's been others who have performed site response work at Treasure Island. For example, Afshari and Stewart in 2019, and Tao and Professor Ellen Rathje in 2019. And they both found that by modifying the damping that they use in the viscoelastic theoretical transfer function, that they were able to get R values close to 0.82. So simply by changing the damping, they were able to better predict the site response, because that would bring down the peak and broaden it somewhat. So what we did is we used our 3D model, looking at different areas, to predict the goodness of fit between multiple 1D site response analyses. And when we used an area of 400 meters by 400 meters, which is this area here, which is quite large, by the way, 400 meters by 400 meters is a large site. When we did that, you can see that the amplitude of the theoretical transfer function, the green line, was brought down quite low and better matched the empirical transfer function. So good, in fact, that we achieved an R value of about 0.87 when we incorporated a 400 meter by 400 meter area. The width, though, is still under predicted. So what we did is we decided to increase the size of the area that we considered to be significantly larger. And we kept changing the size of the incorporated area from maybe, 800 meters by 800 meters up to the full size of the island, which is, quite large, over 1.5 kilometers. And eventually, when we included the full area of 1,600 meters by 1,000 meters, we achieved a Pearson correlation coefficient of greater than 0.9. So that's this kind of pink line right here, magenta. And you can see that as we started to incorporate some of the influence of Yerba Buena Island into our ground motion analyses, that we were able to widen this peak, which better matched the empirical or recorded transfer functions. And yet, by doing that, we don't mess up the high frequency predictions. So this is really quite a novel approach to incorporating spatial variability in 1D ground response analyses. And we were able to achieve much better results than any previous studies at the Treasure Island downhole array. One thing I would stress, this then says that the site response recorded at Treasure Island, which is quite a 1D site, is influenced by the material properties over 1 kilometer away. And that's something that probably nobody wants to hear, because that says that when we're doing our ground response analyses, we probably need to be incorporating spatial variability into them from quite far distance from our actual site. So how does our approach compare with other ways that people use to account for shear wave velocity variability in 1D ground response analysis? So we investigated 5 methods: VS randomization, called Toro randomization; travel time randomization, which was proposed by Passeri and Sebastiano Foti; a surface wave approach, where we incorporate spatial variability from multiple VS profiles from surface wave testing; our H/V geostatistical approach, which I just showed you; and then changing the damping in the 1D ground response analyses. And I'm going to kind of cut this short in terms of explaining the shear wave velocity randomization. Suffice it to say that we have stochastic models where we can randomize shear wave velocity as a means to account for subsurface variability. This approach is used very commonly in probabilistic seismic hazard analyses for critical facilities. Through this Toro randomization approach, we can develop suites of VS profiles. For example, when we apply Toro randomization at Treasure Island, you can see that we're able to recover. There's 250 randomized VS profiles here in pink, and their median is a very close representation of the base case profile, which is measured using PS suspension logging. So the problem with Toro randomization that many have found is when you take the median of all of these 1D ground response analyses from the 250 VS profiles, you often get really excessive overdamping of high frequency response. And sometimes the variation in the fundamental frequency is so large that it causes your peak to be widened too much and not represent the true site response. So we applied shear wave velocity randomization at Treasure Island. We also used travel time randomization. And again, I'm running low on time, so I won't show you all of the details, but the travel time randomization worked quite well. It didn't overdamp the high frequencies, and it brought down the amplitude, the peaks in the theoretical transfer functions. In fact, some might say that it doesn't give you enough variability if you use the recommended parameters for the randomization, but it performed very well at Treasure Island. The surface wave approach, you can use numerous suites of shear wave velocity profiles developed from active and passive surface wave measurements, and you would only choose surface wave profiles that fit within the experimental bounds of your dispersion data and have approximately the correct fundamental site frequency. And when we applied that approach at Treasure Island, we used a bunch of different arrays, microtremor arrays up to 800 meter aperture, and several MASW arrays spread across different locations close to the borehole. And these are the shear wave velocity profiles that we developed from surface wave inversion. And when we studied the site response from those VS profiles from surface wave inversion, we found that they also performed fairly well and didn't overdamp the high frequencies. But perhaps there wasn't enough spatial variability in the area that we considered to bring down the amplitude of the theoretical transfer function. When we consider all of these methods, we already talked about the H over V geostatistical approach, so I'm going to skip that briefly here. I'm going to go to the last approach, which is increasing the damping. So normally we would use small strain damping in our linear viscoelastic ground response. And that small strain damping would be predicted from, say, the Stokey and Darendelli curves as a function of material type and confining pressure. But Tao and Rathje investigated increasing damping measured in the laboratory by 3 times and 6 times. And when we increase damping, we're able to bring down the fundamental peak in our theoretical transfer function, which better matches the empirical transfer function, but we've seriously overdamped the high frequency site response. So let me show you a summary of these results. So here we have Treasure Island, and you have in gray the empirical transfer function. This is the green line is the ground response from the single shear wave velocity profile measured at the site. We then look at the correlation coefficient and the transfer function misfit for that green line, and we enter and add the VS randomization profile. And you can see that by including shear wave velocity variability, we increase the correlation coefficient, but we actually decrease, or we make the transfer function misfit worse. So depending on the metric you use, you could say that we either improved the site response or we made the site response worse. When we use Passeri and Foti's travel time randomization, we increased the correlation coefficient and made it better. And we also reduced the transfer function misfit and made it better. So in this case, it worked quite well, the travel time randomization by Passeri and Foti. When we use the surface wave approach, we increase the R value, which is better, but we decrease the transfer function misfit quite substantially. And so there's somewhat mixed results saying that it could be better than the travel time randomization, but it could also perform not quite as well, depending on the metric you use to judge success. our H over V geostatistical approach, we get the best R value and the lowest transfer function misfit. So it performs extremely well. And when we do the damping modification, we increase R, but we do not significantly decrease the transfer function misfit. So again, there's kind of mixed results with damping modifications. I see that I'm virtually out of time. We've also done this at a different site, Delaney Park, which I don't have time to talk about. But in general, the approach that always works the best so far is our H over V geostatistical approach when we consider all reasonable methods of incorporating spatial variability. And I'm respectful of the time. I'm going to stop now and just say that we are working towards implementing these pseudo 3D models in actual 3D site response. And that's, of course, the ultimate goal. But because we can't perform 3D site response everywhere economically, the H over V geostatistical approach, I think, is really promising for still using 1D site response analyses, but being able to more realistically incorporate spatial variability. And with that, I will end the presentation. There's some references here for those who are interested. I'd like to acknowledge funding by Pacific Gas and Electric for this research. And if you need to get in contact with me, here's my contact information. So thank you very much for your time.
Thank you, Professor Cox. It was indeed a very nice presentation. Really, I enjoyed the lecture, your presentation, particularly some of the very interesting points which you brought out, highlighting the influence of the soil far away from the actual location where the ground response analysis is considered. And you have brought out with good data. And also you have compared with the low strain responses recorded and compared with that and showed that your approach has got a very promising future, particularly to ambitiously replacing the 3D ground response analysis with multiple 1D responses. It is interesting. It is interesting. And I request the audience and participants to have any questions for Professor Cox, who can now. We have 5 minutes for interaction.
It is question answer, sir.
Vijendra, there is a question in chat box. Please read this to Cox.
Okay.
Yeah, I see the question. Yeah, I can read it. It says, when there is an inversely dispersive VS profile, so a profile with a low velocity layer in the middle, how do you generate the pseudo 3D model? And is the scaling of only thickness acceptable? The answer is probably not. We've investigated different approaches to scaling both VS and thickness, but it's non-unique. And so in cases where the velocity profile is more complex, you might have to spend a little bit more time making sure that you use, for example, boring logs to help constrain what you're doing using knowledge of local geology. And for an inversely, an inverse low velocity layer, you're probably going to have to be a little bit more careful because that's a situation where things may not be as simple. So, as in all things, there are simple cases and there are complex cases. And in the complex cases, you're just going to have to be a little bit more careful. But we find that if you develop a shear wave velocity profile that matches the fundamental site frequency, it's less critical that it's absolutely correct, as long as you have something that you are matching the site frequency that has reasonable layering and reasonable stiffness. I have another question. In the graph of the coefficient of R in area, the value of R is somewhere decreasing with the area and somewhere, so increasing and decreasing, correct? Can it be decided what would be the optimum area for the highest value of R? So we've studied that, and indeed, sometimes as we increase the area, we got slightly worse results until we increased the area to a certain point, and then the results got better again. We have to be careful about reading too much into the R value because it's only one metric of showing the goodness of fit. And what we found, and I didn't show this, is that the misfit continuously decreased as we incorporated more and more area. So while the R value fluctuated up and down a little bit, the transfer function misfit actually continuously decreased. And we talk about that in our paper, and I gave the references to the paper. They're at the end of the presentation.
Anybody?
Yeah, I have one.
Yeah, Professor Jack.
Yeah, Professor Cox, it is indeed an excellent presentation, very informative and also thought-provoking. What I'm saying is thought-provoking. Initially, yeah, I scared, frankly, like you said, 1D analysis is not going to work out. Even the anomaly at 1 kilometer can affect. So that is really scary. And then at the end, of course, you gave a solution. Wonderful. My query is like in the beginning, you told about the 3 approaches to come up with the pseudo shear wave velocity profile. That is essentially based on only the fundamental period. And finally, you adopted reducing the thickness of the layer. So in coming up that pseudo velocity profile, can't we use the amplification of HYV along with maybe the damping based on the thickness?
So yeah, there's one school of thought that says that we could invert the H over V data at every sensor location and develop a 1D velocity profile beneath each receiver, and that might provide some useful information. It's possible. I live in the camp, so to speak, where I do not completely believe that you can invert H over V curves to get a velocity profile. Because in my experience, which has been quite significant, the amplitude of the H over V curve can vary depending on which instrument I use, whether it's a broadband seismometer or say a 4.5 hertz geophone. It can vary depending on the coupling, whether I've set it on the ground or whether I bury it in the ground. It can depend on the noise, the strength of the noise. Sometimes it varies from day to day or from daytime to nighttime. And so I don't trust H over V amplitude as much as some people do. Some people trust it a lot. My experience has been that it's not extremely reliable, but if not, the frequency is usually very consistent. And so I prefer to trust the frequency and maybe use the amplitude as a guide. It's a good suggestion, but not to believe it too much, perhaps.
Very interesting. It seems there is a lot of scope for someone to explore how that amplitude can be varying, and with respect to whatever you said, instrumentation or the seasonal variation. Yeah, okay, thanks a lot.
You're welcome.
Anybody?
So I have another question in the chat. It says, do you filter the raw data that you get from the sensors? So yes, the empirical transfer function that we're calculating from the recorded ground motions, we only use a frequency range where we have a signal to noise ratio greater than 3 dB. And so we don't filter anything within that frequency range, which was about 0.5 hertz, a half a hertz, up to 10 hertz. But we filter everything outside of that frequency range, and we don't use that in the calculations of our transfer function misfit. So very low frequencies and very high frequencies we have filtered and not use those in our computations.
What was the fourth or fifth mode frequency of the Treasure Island downhole array?
The fourth mode frequency?
Yeah.
Let me
Is
quickly.
it
Oh, it's like less than 10 hertz. Yeah. So I'll quickly go to those results and I'll tell you real quick. So the fourth mode frequency at Treasure Island is only about 5 hertz. Yeah.
So
it's a pretty soft site. It's a really soft site.
Yeah. Filtering has not affected those modes.
That's correct.
Yeah, you just one follow-up question. Actually, in your presentation, you gave importance for higher modes. And most of the time, our primary structures are influenced by the fundamental mode. Maybe auxiliary structures, maybe, I'm not sure, but up to like, what is your take on the modes? Up to what mode one should go?
So we, like you said, the fundamental mode is most important, and we need to get that right for sure. After that, we need to start worrying about the higher modes, and depending on the stiffness of the structure, like for really soft sites, and if you have small structures, those higher modes can be very important, because if you have a stiff structure on a soft site, you know, you might have a really long period or low frequency fundamental mode, and you're never going to build a 30-story structure or a really long bridge on that site, but you're going to build some 4 or 5-story, you know, buildings, apartment complexes or whatever. And so those buildings that are shorter are going to be influenced by the higher modes. So we just need to be careful and not neglect the higher modes, because they can be important. And so fundamental mode is most important. And then after that, we have to start considering the match between those higher modes and the actual resonant frequency of our structure.
Thank you.
One last question, Professor Cox. In the pseudo velocity profile which you adopted to get the transfer function, what was the damping ratio used, minimum damping ratio used? Was it from Stokes, Darendelle?
Yes. That's correct. Yeah, so when we did our normal 1D site response analyses without modifying damping, we used d-min from Stokes and Darendelle, and so it varied as a function of material type and confining pressure. But you know, d-min would have typically been on the order of 1% to 2%, depending on whether it was clay or sand. And then when we modified damping using kind of Rathje's approach, we would take that d-min and multiply it by a factor of 3 or a factor of 6 in order to bring down the amplitude of the fundamental mode peak.
Sorry, Chair. One last question, just from my side.
Yeah.
Just one last question. Professor Cox, I couldn't able to understand whether it seems you used linear analysis. Am I right?
Yeah.
That is correct.
But why not? Normally we use equivalent linear analysis. What is the level of motions you used?
So when we chose our ground motions, and there's so much information, I didn't have time to present everything. We used only ground motions in this part of the study that had PGAs less than 0.05 G. Okay, so they were definitely in the linear elastic range. And we chose to do that because we want to study the impact of spatial variability without the overlapping complications of modeling nonlinearity. So we can do both, and we have done both, but we chose in this particular study to focus only on the impact of spatial variability, So we didn't have to study soil nonlinearity, which gets much more complicated.
Oh, wonderful. Excellent work. Very extensive and innovative. Thank you.
Thank you. Thank you. I appreciate the invitation.
Thank you, Professor Cox. Indeed, it really opened up the field for our young earthquake geotechnical engineers who are doing the research to look in this direction also, so that one-dimensional ground response analysis still has got some value, which is in recent times has got some negative remarks. Okay, you have brought back its due respect to it. Thank you for that. And now, shall we start the paper presentation with the first presentation by
Paper number 735, sir.
735, Seismic Bearing Capacity and Elastic Settlement of Footing on Slopes by Sukanta Das, Indian Institute of Technology, Roorkee.
Good evening, everyone. Myself, Sukanta Das, Research Scholar at Department of Earthquake Engineering, I.I.T. Roorkee, Uttarakhand. I am going to talk on seismic bearing capacity and elastic settlement of footing on slopes. Now, research background on or introduction on design of foundation, whether it is situated on sloping ground or flat horizontal ground. So, for design criteria aspects, the footing or any kind of foundation should be sufficient enough to sustain the loads coming from the superstructure. That means the load coming from the structure should be less than the ultimate bearing capacity of the slopes, and the settlement of the foundation should be within the permissible limit. When foundations are constructed on the sloping ground, the stability of that slope is come into the picture, which is another additional factor for design of foundation in sloping ground. Different buildings are constructed on the sloping ground. One picture has been presented in the slide, which is located in Mizoram city in India, and several hilly region different types of buildings are constructed, and this recent due to increase of population and lack of land and other aspects, the population of the in this region are increasing. So last past earthquakes damages has also concentrate also take attention to design proper design of foundation or buildings on sloping grounds. Several researchers has did numerical and experimental research are presented as a literature aspect in the table. Whether from the table it can show the much attention is given after few decades. But initially, Mayor of 1957 has started this foundation on sloping grounds. So I'm not discussing about these things. I'm going directly to some last records that Mayor of reported that seismic bearing capacity or plain static bearing capacity. He did only static bearing capacity. Whether footing is subjected to top of the slope or embedded on the sloping face is decreases due to inclination of slopes. Then BIS, Bureau of Indian Standards, suggests that the minimum edge distance of the footing from the sloping ground should be 90 mm, and that this region, this custom line or pressure valve should not intersect the sloping ground, and this should be sloping joining line should not steeper than 1 vertical. That means this angle within the 27 degree. Now, to investigate the seismic bearing capacity on elastic settlement, we have modeled finite element analysis 3D model. Here, this is not a 3D problem. So for that, we have converted 3D into 2D problem by considering the lateral direction is considered as 1 meter, and standard boundary condition has been fixed that the vertical edges are fixed from the lateral direction and fixed from bottom edge is fully fixed from any kind of rotation, and this foundation is located at the face of the slope and the loads coming from the top, and that bearing capacity factor using Q equals to 1 gamma B and N gamma QS. This N gamma Q is a resultant bearing capacity factor taken from Mayer of 1951, and the mesh size varying according its accurate results. So from the results, comparison of results has been shown. The results has observed, obtained from the finite element analysis and presented. Extensive comparison has been showed of bearing capacity factor corresponding to seismic factors. This alpha H is seismic factor, and the present results showing a quite good agreement with all the past studies. And the right side figure is showing as the previous authors or researchers has did several researchers and present numerical analysis comparison has been shown with in good agreement with past literature with seismic condition. Now the effect of embedment and sloping ground. From the figure, we have seen the bearing capacity factor and the sloping angle. If we consider first figure, that is depth of the embedment is fixed 1 and sloping angle 20. First consider phi is constant, 545 degree angle. If the seismic coefficient increases, the bearing capacity factor decreases, which is quite expected as horizontal ground, and similar trend has been found for sloping ground. And also as the internal friction increases, the bearing capacity increases, which is also expected as same as horizontal ground. But as keep in mind that embedment depth is same, but slope angle is changing. See here, the phi is 45 degree and phi is 45 degree. Here it is 100 and it is more than 100. It is in log for axis, y axis is presented the bearing capacity factor. That's why it is coming. But from open eyes view, we can see that the 20 as the bearing capacity factor as slope angle 20 degree is quite high compared to bearing capacity factor as sloping angle 30 degree. However, as the embedment increases in both sloping ground, as the embedment increases, the bearing capacity factor is going to increase for all internal friction. Now, the bearing capacity, the important outcomes from this study is bearing capacity factor increases with the increase of internal friction and irrespective of any other condition. For a constant embedment sloping ground, seismic bearing capacity factor decreases with the increase of seismic forces. And from the previous figure, bearing capacity factor increases as embedment factor increases, which I have already discussed in the discussion of figure. So now move into the finite element modeling of elastic settlement of the footing placed at the sloping ground. This researchers has did several researches, but somehow this is not reported from the past. As per author acknowledgement or knowledge, this elastic settlement has not been reported any other literature. So researchers very concluded and proposed one equation, Bani and Polas, which is very popular for calculating of elastic settlement. This equation here, those are the geometry and soil properties, and those are the influence factor. So first validated the finite element modeling with this past literature. We have this width ratio B by B L small this model width of the domain versus footing width has been correct. We have find that initial at less width domain size, we have find some change in results, but after 50 degree or 30 degree, quite less variation in results. So we have considered this 50 width ratio for horizontal variation validation. Again, here a extensive literature of comparison of the past results has been shown in the influence in terms of influence factor, and also the influence factor has been presented with the theoretical solution available as for flexible footing and for rigid circular. As we know that flexible, in case of flexible circular footing, here the contact pressure is something different. So the maximum settlement can be found at the center for flexible, but in the rigid, throughout the beneath the footing, the settlement is almost equal. So, and from this figure, we have found which is in good agreement and quite reasonable, giving a reasonable results. So now we have computed the effect of sloping angle with the elastic settlement. So here is the reduction settlement at flat ground and settlement and sloping ground corresponding to the degree of slope. So we have found that center for this center and for crest, this center there a variation has been observed, but if we compare, that is very less, whether in case of flexible footing and rigid footing. So from the present seismic bearing capacity and elastic settlement, the major conclusion has been present in this slide. The present results obtained from the FELA analysis for both seismic and elastic settlement of the footing on sloping ground are showing good agreement with past studies. However, seismic bearing capacity obtained by the limit analysis, whether it is lower bound, upper bound, or finite element limit analysis, are quite less compared to FEM analysis. The effect of slope angle has been examined using numerical study, finite element analysis, but no significant has been observed. The variation of elastic settlement has been found 6 to 10% at with sloping angles 0 to 40 degree, what is not quite significant. So within this elastic settle this range, and after 40 degree slope angle with soil angle slope angle 40 degree is not possible. So within this range, the elastic settlement, maybe it is significant in primary or secondary or different settlement, but within the elastic settlement, that sloping angle has not significant influence. Now the bearing capacity factor decreases with increase of seismic forces in horizontal sloping ground. As we know, the bearing capacity factor decreases seismic, whether it is pseudostatic or any dynamic forces, the bearing capacity factors always reduces. But the constant load and footing geometry, the bearing capacity factor decreases as slope angle increases. That means whether the hilly region, with the sloping angle is influenced significantly to determine the bearing capacity factors in the footing. For a given for the given slope angle, the bearing capacity factor increases with the increase of footing embedment. Due to this, as in the horizontal, we have observed that bearing embedment increases, the bearing capacity factor increases. In the same phenomena has been observed in case of footing situated on the sloping ground. That may be because of the participating soil or the soil mass involved to support the loads coming from the superstructure is participating in larger compared to shallow depth. As embedment increases, the bearing capacity factor is also increasing. Finally, the for estimation of seismic bearing capacity factor, design charts or set of bearing capacity factor has been presented, to which will be helpful for practitioner or site engineer or researcher to evaluate or to check the seismic bearing capacity factor on sloping ground with corresponding to phi value and sloping angle. And those are the reference which has been used for present research. And thank you.
Thank you, Das. We have 2 minutes for interaction with Das. Indeed, your presentation was good.
Thank you.
And if any participant has any questions, they can ask. Professor Jakka.
I have one question.
Yeah.
I have one question. Mr. Das, you are highlighting about the safe slope angle of
Yes.
27 degrees.
Yes, sir. That is recommended by the BIS 1904.
On what basis it is?
Actually, sir, in my PhD work, I'm going to, I have investigated this, why they have recommended, but no literature has discussed these things. But from our research, we find that beyond that angle, that frustum angle, what I have shared earlier, the slide, that frustum, that load, the dissipation load, or the kind of pressure bulb, the pressure bulb generating beneath the foundation is should not cross that sloping surface. That sloping surface is there, and that pressure bulb is generating, that surface should not cross that sloping angle. So approximately after several experts' opinion, or maybe it has considered that it should near about 30 degree. But again, from our studies in extensive study, we have found it is rather it should not be 27 degree or 30 degree. It should be depends on sloping angle beta. But as per BIS, it is recommended that it should be 27 degree.
So that's why it also depends upon the type of the footing, whether you are using this raft or rectangle footing or square or circular. So this will also matter because of your variation in the pressure bulk. I know that various literature in the literature, people have recommended 27 degree, and we have done at our university some experiments also. We are also getting the 27 degrees. Anyway, it is a long story. It is still under publication. We will
Yes,
come on. Thank you.
Anybody else? Dr. Chandra Bogi Reddy.
Hi, so I have one doubt, one question.
Yeah.
So what kind of parameters you consider in the FEM analysis, either drain and undrained condition?
So, we have not considered any water table. This is for dry condition.
Anybody else?
Any questions from audience, remaining delegates?
I have one basic question, that's fundamental. How you have defined the seismic bearing capacity, particularly in FEM analysis? Is it obtained from the load displacement curve? You have mentioned in your paper that uniformly distributed pressure is applied on the foundation. How you have defined your seismic bearing capacity in Plaxis?
Yes, sir. In Plaxis, there is on pseudodynamic, pseudostatic approach has been adopted, and there we have applied seismic coefficients. Those coefficients has been presented in the paper, and corresponding to that, we have found that bearing capacity factor from load settlement curve, and from those results we have also computed by finite element limit analysis. But in this paper, we have presented only finite element results.
So I have a doubt that can you really call that as a seismic bearing capacity? Because it is a pseudostatic analysis. Can you call that as a, because I think if it is seismic bearing capacity, then some dynamic load should have been involved and load settlement curve. Okay, you can, for bearing capacity, you can evaluate. Yes. From the codal procedure, load settlement curve, whatever you want, you do. But that load settlement curve should have been obtained using some dynamic load with soil structure interaction.
So that's what we are doing.
Should have been a validated one. I have my reservation to call that as a seismic bearing capacity. Anyway, it opens for further discussion. If any other participant wish to get any clarification, please go ahead. We have 30 seconds time. Okay. If
you can unmute and you can raise your question.
Yeah. Chat box, there is no question.
No question.
Okay.
Shall we go next?
Yeah.
Next presenter, paper number 737, sir.
Comparative study on behavior of vertical and batter piles in lateral spreading soils by Rajeshwari, Indian Institute of Technology, Dhanbad.
Good evening, everyone. My topic for today's presentation is comparative study of behavior of vertical and batter piles in laterally spreading soil. This
So they have to mention whether the student or faculty.
Sir, I am a student. Sir, I am a
you have to mention.
At I.I.T.
You have to always mention.
Okay, sir. Sir, I am a research scholar at I.I.T. Dhanbad.
Okay, please continue.
Pile foundations are vulnerable to damage due to liquefaction-induced lateral spreading of the ground during earthquakes. Under such situations, battering of piles may prove to be an effective option. This is because the batter piles transmit additional lateral loads by axial tension or compression as compared to a same dimension vertical piles. However, there is no clear evidence of its effectiveness since both beneficial as well as performance have been recorded in past earthquakes. This figure shows the lateral load transfer in batter piles, and the pile which is inclined in the direction of loading is termed as a positive pile, and that inclined in the direction opposite to the loading is termed as a negative batter pile. This study has four major objectives. First is the comparative evaluation of the behavior of vertical and batter piles in laterally spreading soil through probabilistic approach. Second is to study the effective shape of PY curves used for the liquefiable soil on the pile response. Third is to develop the predictive models for the maximum bending moment for single vertical and batter piles. And final one is to evaluate the probability of failure of soil pile systems. In our study, we have considered single board piles of diameter D and length L, which is embedded in a 3-layer soil profile as shown in this figure. And the water table is assumed at the interface of the liquefiable soil and the non-liquefiable surface crust. In the study, we have not considered the effect of inertia because the inertia forces are negligible in the post-liquefaction stage. So we have adopted beam foundation approach for developing the numerical models of the system. All these models are analyzed in finite package. This figure 1, figure A, shows the typical soil pile back the TZ and springs are estimated using the equations which are available in the literature. Here I'll be discussing only the PY curves for the liquefiable layer. So traditionally the PY curves for the liquefiable layer is obtained by reducing the PY curves for the non-liquefiable soil using appropriate reduction factors known as P multiplier. So in my study, I have considered the P multiplier value suggested by Brandenburg 2005. These PY curves have a strain softening behavior, and you can see the figure B shows a typical concave PY curve. On the other hand, the PY curves, which are back calculated from the element and the field test, indicated a strain hardening behavior. These PY curves are convex downward in shape, and figure C presents a typical convex PY curve for the liquefiable soil. And this strain hardening behavior is due to the dilative behavior of the liquefied soil when subjected to the shear loading conditions. So the lateral resistance of the batter piles are not well defined in literature. So modification factors which are suggested by Zhang et al. 1999 to consider the effect of batter on the pile resistance of vertical piles. And it is also assumed that the configuration of the PY curve is same as that of the vertical pile. Ground displacement. In this figure, we have assigned within the liquefied layer and a constant value throughout the surface crust. This is because once the soil liquefies and it starts moving, the surface crust moves as a single unit. The ultimate field ground displacement value using the equation proposed by Hamada et al. 1987. Selection of input parameters and consideration of variables. So here in our study, we have considered the pile properties to be deterministic, and the piles are assumed to be made of M30 concrete with 0.5 meter diameter and slenderness ratio of consider different batter angles, represents a vertical pile, and 10 degree and 20 degree, both positive and negative batter piles. The baseline properties is also assumed to be fixed at a relative density of 80%. The various random parameters and the associated variability were estimated based on the information available in the literature. This table presents the various random parameters considered, and its axis we have considered 5 variables: relative density of surface crust, thickness of surface crust, relative density of liquefied sand, liquefied layer thickness, and the ground slope. Proceeding to the probabilistic study, we first investigated the influence of shape of PY curve on the pile response in the soil. For this, considered a vertical pile of slenderness ratio 3 embedded in a sloping ground with 6 meter thick surface crust overlying a 4 meter liquefied layer, 0.5 meter layer, And figure B shows a soil reaction profile for both convex and concave PY curves. From the figure, we can observe that for both the PY curves, the soil is mobilized to the ultimate resistance within the liquefied layer. And from figure C, we can observe that the bending moment, which is calculated using the convex PY curves, is several times higher than that obtained using the concave PY curves. So this confirms that the shape of the PY curves used for the liquefiable soil plays a pivotal role in influencing the pile response in laterally spreading soil. So hereafter, all the piles are analyzed using the convex PY curves. Major steps involved in conducting the study. First, we have to define the response parameter, that is maximum bending moment. Then we have to fix the various factors and the levels of each factor. For our study, the upper limit and lower limit of the each factor is considered as the levels. Then we will construct an experimental design matrix for using the factorial design methodology. So using this matrix, we conducted various analysis, and then prediction models were developed. So once the prediction models were developed, the probability of failure of the soil pile systems were calculated using the Monte Carlo technique. This figure shows the effect of the maximum bending moment. These plots are known as the main effect plots. It is the mean response at the lower and the height of each parameter. And from this figure, we can observe that the maximum bending moment increases with increase in the thickness of the surface crust, increase in the relative density of the surface crust, relative density of the liquefiable layer, and the slope, but it decreases with the thickness of the liquefiable layer. So based on the analysis which were conducted using the factorial design method, we developed the predicted models using multiple regression analysis, and then we came up with this equation, which is the model maximum bending moment of a pile in a laterally spreading soil. And this table shows the coefficients of the for piles of different batter angles. These coefficients were estimated using the method of least squares. This figure shows the effect of various random parameters on the probability of failure. So as I explained earlier, the probability of failure was calculated for the system using. From the first figure, we can find that for all the cases considered, the probability of failure increases sharply when the thickness of the surface crust is more than 1 meter. But if you see in the case of positive probability of failure is 1% when the thickness of the surface crust is than 1 meter. But if you see the vertical piles and negatively inclined batter piles, the probability of failure is higher even in the absence of the surface. The second figure shows that the probability of failure is increase in the thickness of liquefiable layer. This is because with higher thickness, the ultimate strength for convex PY curves provides better resistance in the so this acts as a buffering effect on the movement of the piles. So if you see these two figures, it shows that the probability of failure increases with increase in the relative density of the liquefiable layer and the slope of the ground. Even though the change is negligible, very less in the case of density of liquefiable layer. The PY curve used for the liquefiable layer has significant influence on the lateral spreading ground conditions. We have seen that the conventional curves underestimate the pile response, pile bending moment in laterally spreading ground. This is positive batter piles are effectively limiting the pile bending moment, and the reduction in this bending moment increases with increase in the pile batter. And finally, the risk posed by the surface crust thickness is most for piles with batter angles. These are the major references. Thank you.
Yeah, nice presentation. I have one small suggestion and one doubt. In the second slide, you mentioned nearly 5 objectives in one paper. So can you define all the objectives? You mentioned nearly 5 objectives in one paper. Can you go through the first slide?
Oh, sure.
So can you address with all these more?
So this slide. Sir, first is a comparative evaluation of behavior of vertical and lateral piles in the spreading soil. And in our study, we have found that the positive battle piles give a better performance compared to the negatively inclined battle piles and the vertical piles. Second is a study of the effective shape of PY curves used for the liquefiable soil. And from that, we have found that the conventional concave PY curves underestimate the pile response in the laterally spreading soil. And the third is that we have developed prediction models for maximum bending moment for both single and vertical and battle piles. And finally, we have calculated the probability of failure of the soil pile systems.
Okay, and next one more my doubt is at 14th slide, only for two values you mentioned like a graph kind of. So can you just verify it?
Yes, sir. Actually, these plots are the main effect plots. It gives the mean response at the higher and the lower settings of each parameter. In my study, for each parameter, I have considered two levels, lower limit and the upper limit. So this graph gives the mean response at the lower limit and the upper limit of the each parameter.
Okay. Thank you. Vijendra sir, please.
Thank you, sir. Thank you.
Yeah, I don't have any question, but if any other participant wish to. Yeah, I think we can move to next paper.
Thank you, sir.
Thank you, Rajeshwari.
Thank you.
Thank you, Rajeshwari. So next paper number is 740.
Transient response prediction of shallow foundation using FIS by Suvendu Kumar Sasmal, NIT Roorkee. Yeah, Suvendu.
Yes.
I think you can.
Sir, is it visible, sir?
Yeah.
Yes, sir. Yes.
Good evening, Honorable Chair and Co-Chair, respected Brady Cox and other participants. I am Subhendu Kumar Sasmal, a research scholar of Department of Civil Engineering at the National Institute of Technology, Roorkee. I am presenting a paper titled Transient Response Prediction of a Shallow Foundation using NFIS. Shallow foundations are normally subjected to static loads. As it is well known in the case of dynamic load, there are two phases, transient behavior and steady state behavior. In existing literatures, it is found that when studying the behavior of a shallow foundations under cyclic load, the settlement of a shallow foundation due to fast load cycle is generally ignored, and after the steady state settlement response is generally reported in literatures like Raymond and Comas 1978 and Das et al 1995. Hence, it is a matter of interest to observe what really happens during that fast load cycle, which is the main objective of this study. In this study, a soft computing method and FIS has been applied to observe the settlement due to fast load cycle. These are some of the literatures where ANFIS has been used in geotechnical engineering area. It is found that the application of ANFIS in a soil dynamics problem is very rare. So this is another motivation to use the ANFIS method in this problem. In this problem, a shallow foundation is modeled using beam and nonlinear nuclear foundation model, which is done using open system for earthquake engineering simulation, OpenSys. In this model, the soil structure interface is modeled using three springs, UZ simple springs, TY simple springs, and TZ simple springs. Those are used to capture the vertical response, passive response in the case of embedded foundation, and the sliding response of foundation. The soil properties which are used in this study are a published result. 3 types of sands are used. For loose sand, the published soil parameters of Sahu et al. Are used, and for dense and medium dense sand, published results of Patra et al. 2012 are used. The dynamic soil parameters such as Young's modulus and Poisson's ratio are calculated from EPRI manual 1990. While modeling the shallow foundation, the following steps are followed. First, footing and soil nodes are created. Then footing nodes are joined using elastic beam column element which are one-dimensional, and non-linear springs are used to connect footing node and soil node. The stiffness of the springs are calculated using the well-known expressions of a Gazettas, and the distribution of springs has been done using the procedure mentioned in Haddon et al. It is noteworthy that the bearing capacity of the springs is calculated using Horv 1963. After the footing and soil are modeled, then load is applied. First, static load is applied. An allowable static load is applied by dividing the ultimate bearing capacity by a reasonable factor of safety. Then after applying the allowable static load is kept constant. Then one cycle of a cyclic load is applied. The intensity of a cyclic load is some percentage of the ultimate bearing capacity of foundation. After the numerical model, the same footing was simulated using Plaxis 3D using more Coulomb model for same soil parameters, and it is found that the OpenSys or finite element results and the more Coulomb results are in very good agreement. For unfished modeling, first a footing on cohesionless soil is modeled using beam on nonlinear Winkler foundation. 3 types of soil as discussed are taken. The depth of embedment by the footing width ratio is taken as 0, 0.5 and 1, and 4 factor of safety values are also taken, 2, 2.5, 3 and 3.5. The intensity of a cyclic load is 5%, 10% and 13% of the ultimate bearing capacity of the foundation. In such a way, in total 108 number of data sets were generated, which are analyzed using UNFISH. Then, after developing the UNFISH model, a parameter significance analysis was also performed to determine the most influencing parameters. In UNFISH, there are 5 layers where X and Y the starting are inputs. The layer 1 is the membership function layer. The membership function is an innovative procedure to determine the involvement of each input parameters. It was first introduced by L.A. Jade in 1965 in his first research paper, fuzzy sets. After that, in the second layer, firing strength of fuzzy rules are calculated by multiplying the input value and the corresponding membership functions. In layer 3, the normalized value of firing strength is calculated, that is by dividing individual firing strength by summation of all the firing strengths. In fourth layer, the normalized firing strength is multiplied with a factor F1 or F2. These factors are functions of parameters which are generally obtained after training the UNFISH model, which are also known as consequent parameters. Then these W and F1 parameters are summed up to find out the final equation of UNFISH. This UNFISH architecture was proposed by Zhang in 1993. This is the structure of a present ANFIS model where 4 inputs are there, and for each input 2 membership functions are there. There are in general 2 methods to determine the number of rules. First is grid partition and second is subtractive clustering. In this method, grid partition method is used, that is 2 to the power 4 means 16 rules are there. Here, generalized bell-shaped membership function is used, and an approach of 150 is found to be sufficient for the complete analysis. After developing the ANFIS model, the predicted settlement is are compared with the settlements observed from the OpenSys analysis. It is found that for both training data and testing the data, the coefficient of a determination is 0.98. That means the model is not only well trained, but it has a very good generalization ability. It has the ability to predict well outside the training data. Parametric analysis of each individual parameter on the effect of each individual parameter on the output is shown in this graph. It is observed that apart from input 3, which is the intensity of a cyclic load, all the other parameters inversely influence the settlement, transient settlement of the foundation. This is due to the fact that with the increase in relative density or depth of embedment of footing, the footing becomes more stable, and for same cyclic load, the settlement will be less. This is a 3D version of a surface plot that shows the combined effect of 2 inputs on the output. In this approach, while using 2 inputs, the other 2 inputs are kept constant to their median value, and these 2 inputs are varied from lower range to higher range to study the influence on the output. Sensitivity analysis is performed using a procedure which was mentioned in Beura and 2018. This using the equation given here. In this equation, DI represents the range of influence of a input parameters, which can be calculated for each input parameter by keeping all the parameters to mean value and calculating the output for highest value of the input and then lowest value of the input, then subtracting the values. By this approach, we will know the range by which the input is influencing the output parameter. It is found that factor of safety is the most influencing parameter, followed by intensity of cyclic load, depth of embedment, and the relative density of soil. So in this study, a dataset was generated using beam on nonlinear Wickler foundation model, and first the beam on nonlinear Wickler foundation model was validated against Moore Coulomb model. After that, transient settlement analysis was done. It is found that ANFIS can be used to predict successfully the transient settlement. The non-dimensional transient settlement is directly proportional to the intensity of a cyclic load and inversely proportional to the factor of safety, embedment factor, and the relative density of soil. Sensitivity analysis of a trained ANFIS model suggests that factor of safety is the most influencing parameter and the relative density is the least influencing parameter. These are some of the references. Thank you.
Yeah. Good presentation. So I have one doubt about and one question. So in Moore Coulomb, which parameter you use in the drain condition or undrained parameters in FEM? In the FEM analysis, so
Drain
CPI
parameters.
drain parameter.
Yes, sir.
So in laboratory, you tested in the laboratory or you taken from the literature review?
Which parameters are I am not getting?
CPI parameters. How you consider these CPI parameters? Suvinder, can you hear my voice?
Yes, sir. Yes, sir.
Yeah, so I have a little doubt about that one. So how you consider the CPI parameters in the FEM analysis?
So in that FEM analysis,
Yes.
the nonlinear equations for modeling springs were reported by Boulanger in 1999. In that equation, for each UZ simple, TZ simple, and PY simple springs, the nonlinear response can be coded in C++ using those equations.
Okay, I mean my straight question is how you consider the CPI parameters, the drain condition and drain condition. In laboratory, what are the tests you perform?
In laboratory, I have not done the test.
Okay. You taken from the literature review.
Literature.
Is it? Okay. So, and one more question: why you want to use the Moore Coulomb method to compare the result? Why you want to choose Moore Coulomb? Any reason behind it?
Because in hardening soil methods and HSmol methods, there are so many assumptions. In this study, in cyclic response study, those assumptions are not accurately done. In Moore Coulomb method, there are less assumptions, and it is found that the more the assumptions and the more complicated is the model.
Nice. Have any doubts from any queries from audience?
Yeah, one on the chat box is there. One query by Neeraj Kumar Das.
Can you go through the chat box?
Yes, sir. He has asked, ANFIS is FEM based or AI based? So ANFIS is AI based. It is a data-based approach.
Any other participant? So, what is the cyclic load characteristics you have used for the analysis?
Cyclic load is of rectangular pulse character, which has a frequency of 1 cycle per second and intensity of 5, 10, and 13% of ultimate bearing capacity of respective conditions.
Is how many cycles of loading?
1 cycle.
1 cycle. So there is the transient
yes, sir.
Pulse you have used. Rectangular pulse. Cannot call it as a rectangular pulse you have used. Of the frequency, what is the dominant frequency?
1 Hertz.
1 Hertz. What was the frequency of the foundation soil system evaluated by Geostatistical equation?
I have not calculated that.
How you have incorporated the mass of the soil associated with the response of the footing?
Mass of the footing is assigned to the center of the footing.
No. Mass of the soil participating in the response.
Actually, in the BNWF model, mass of the soil is not considered because it is the spring represent the interface.
Thank you, Suvendu. Anybody else? So, sir, I request my coach.
I think it is a nice presentation. So, shall we go to the next presentation, sir? Hello.
Next one is experimental and numerical study of shallow foundation subjected to vertical dynamic load by Das NK, IIT Kanpur. Yeah, Das, you can proceed.
Yeah, okay.
1 minute. Govindraju, the clock is not showing now.
Here I am on the clock, sir, no problem.
Sir, I am audible?
Yes, yes, it is audible.
Okay, yes, sir. So, sir, myself, Neeraj Kumar Das, I am a research scholar in IIT Kanpur. So, my paper title is Experimental and Numerical Study of Shallow Foundation Subject to Vertical Dynamic Loading. So, just a minute, sir. So, the contents of the presentation is like this. So, I will start it. So, basically, at the field site, we have a model footing. We vibrate is by a lesion type eccentric mass shaker. So basically we will be giving some harmonic force. So as a result, we are getting some harmonic displacement or velocity or acceleration. So the concept is kind of the machine foundation should be maybe subjected to periodic loading. So it should be well designed. So the dynamic displacement should be in visible range, and based on the mass we can add or subtract so that the less vibration in the practical field case. So basically this is also known as field vibration. So I just a small literature review. So the first expression is given by the regional. So he has given for a circular disk like what is the magnitude of the dynamic displacement is there. So Lisman has given the expression for the spring and despot. Bhaumik in IIT Kanpur have considered the various cases, and Bedya and Rathi have considered the effect of soil layering. Swan and Ghosh has used kind of a, they vibrate it and see the effect other. So active and passive footing. And Das et al. Myself have also studied the machine foundation earlier. So the inside machinery of eccentric mass shaker is as shown. So this A diagram is actually, this is a helical screw. So this knobs actually moves. So what happens ki there is some eccentric mass is there. So of 1.54 kg. So it rotates at some eccentricity, which is vary from 0 degree to 180 degree. So that the maximum force is 10,000 kilogram force. It is equivalent of 100 kilonewton force magnitude. So based on the capacity, or we know the mass of the footing, we know the mass of the oscillator. So we can have the range so that we can calculate the dynamic characteristic of the foundation soil system. First model footing is cast. So this dimension is 1 meter by 1 meter width and length, and the depth is 0.3 meter. So after this, we have drawn a pit, because in earlier literature review, it's a 2 times a pit is recommended. So this is the footing. We place a block vibration over it, and this is moved by the DC motor. So in data acquisition system, we have placed the accelerometer sensor. This is piezo based accelerometer, or say strain gauge based. So we place at the edges, at the 4 edges of the footing, and also at the center. So basically with this eccentric mass shaker comes a MEMS based sensor, which actually give good reading at very low frequency, but when we move at high frequency, it is not giving good. So that's why we have to place so much sensor and connect it to the National Instrument data acquisition system. So this is the real photograph. So acceleration 1, 2, 3, 4. So 4 edges. So we can have an average and see and compare it with the just this is on the center. So what is the force generated? So it follows like mv square upon r, basically a centrifugal force. Then we know velocity r omega, so it becomes a me omega square. So basically me is me sine theta by 2. So if we put is the eccentricity, say we fix the eccentricity, say 20 degree, then we vary the frequency, say from 5 hertz to 43 hertz at every 2 hertz. So to have a peak response of the foundation soil system. So what is the experimental procedure? So we have some reading from MEMS based, because it will give direct, but this is not giving accurate. So we have placed strain gauge based. So the sampling rate of it is 2000 sample per second. So say for 20 second, for 15 second, we store the data, then proceed it. So Nyquist frequency will be 1000 hertz. So we can capture up to 1000 hertz. So we have recorded the accelerometer, then calculated the velocity by integrating, then displacement. So by double integrating the acceleration, we would get the dynamic displacement. So this curve is taken from Richard et al. Famous vibration book. So this is a famous method to find the FMR, machine resonating frequency, and FN, the natural frequency of the soil. So basically FMR is greater than FR. So this method is used to find the damping ratio. So this is a diagram. This is for E20 degree dynamic displacement. This is for 40 degree. This is for 60 degree. So we can see that by increasing the force, the dynamic displacement is increased, which is obvious, but it is happening at, say, lesser frequency. So this clearly shows the soil is non-linear. It is first noted down by Novak in 1970. So this is the frequency response function, which is basically the FFT of the output. Our output is the dynamic displacement or the acceleration we are measuring, and what input load we are giving from the oscillator. So you can see that uh, just so we can see that at, say, E60, the frequency is around 23 hertz. So from the FRF, if we just compare it, it is also giving 23 hertz for all the four displacement at the edges. So these are in accordance. So how much energy is in stored? So at resonance, the waves go and just bounces back. So it's a kind of an instability system. So we can see the FR is peaking at only at 23 hertz. And this is the input acceleration. Just I have shown like it's a dynamic kind of thing. This is the filter. I have used fourth order filter. And just to show, to understand what resonance is, I have shown 4 diagrams. So this is basically the offset acceleration with time. Sir, this is for 5 hertz, this is for 21 hertz, this is 23 hertz and 41 hertz. For E60, the resonance frequency is 23 hertz. So you can notice the ordinate of this PGA, peak ground acceleration, or the footing or the sensor accelerometer placed at the foundation edge is 0.005 at 5 hertz. At 21 hertz, it's just 10 times increase, 0.5 hertz. And one can notice at 23 hertz, it is around 3. So 3 means a multiple time it has increased. So the greater the frequency, the greater is the force. So we have expected a higher G. So it is around 4. But you can see the sudden jump at the resonance. So the peak ground acceleration is also jumping. So this is the damping value. So damping value I have earlier noted, FMR and FN first calculated by Richard L method. And then for this present study, we have considered 20 degree, 40 degree and 60 degree. So the displacement is increased, which is obvious. The resonance frequency is decreased. So it is also natural. Natural frequency obviously less. So damping ratio is kind of an increase with the increase in force. So we have also compared it the previous study done at IIT Kanpur field site, Bhomik and Swan and Ghosh. So this is actually comparable. So we can notice the displacement is kind of a comparable because we have used a different force. So our machine has a higher capacity. So you are seeing a dynamic displacement of greater magnitude. Now we have simulated numerically also. So in this, first sensitivity analysis is done to fix the domain size. We have varied and notice how the dynamic displacement is changing. So this bigger base, 30 meter by 20 meter, is a soil base. Then there is a this is a pit. So there is another soil of, this is octahedral nature. This soil base of 12 meter by 12 meter, or as at a depth of 4 meter, is taken tetrahedron. So this finer meshing is done around the footing because the all load is applied by the oscillator on the footing.
You have last 1 minute.
Okay. So I am finishing. So basically I came to so basically finer meshing is done around the footing because higher stress concentration is there and at lower. So we have just put the dynamic load. So we are getting, this is the experimental value. Sir, at different force. So we are getting a very close to the experimental value. So in a summary, I can say that with increase in force, the resonant frequency is decreasing. So this shows soil nonlinearity, and this also increases. So while designing the machine foundation, the resonance zone should be avoided, and our numerical model is well capturing the experimental dynamic response. So these are the references, and thank you, sir. Any question? Hello?
Any question from the participants?
I have.
Yes, sir.
Anyway, it was nice, Neeraj, to see that all that oscillator, lesson oscillator to after a long time. Okay, any dynamic testing, it is really enlightening to look at the experimental setup and look at the results. Here you have used the and also many old references, really nostalgic. Lismer, Reisner references, but the output, what you have measured, okay, is it any filtering is used to smoothen the harmonic response?
Sir, actually, because every sensor has some noise by default. So the thing is, I have used the Butterworth fourth order filter, and the cutoff frequency I have used kind of
because
a,
input motion also has got a lot of noise from
yes, sir.
graph we can see.
Yes, sir. So I have varied the frequency, and I observed when I using say 0.17 hertz or point greater than 0.17 hertz, the my signal is kind of smooth. It's a kind of a dynamic. That's why I shown the input acceleration, sir. So this I observed, and my intent, because I know from the previous study the resonant frequency is 33 hertz. So I put a cap maximum at a 45 hertz. So 0.17 hertz to 0.45 hertz I put it. And I also use the Henning window because spectral leakage is there, because this is cause or sign. So what happens, it is not starting from one, say from something less than. So I have also used Henning window, sir.
Anyway, all the outcome of the test appears to be very obvious with respect to nonlinearity and change in natural frequency of the system with the amplitude and all, and also the damping evaluated for the linear case, though you say that it is gone to nonlinearity. Okay, any other question from any other participants? If you don't have, Dr. Chandra, we can move to next paper, I think.
Yes, sir, we will move to second one.
Thank you, sir. Thank you all.
Thank you. Nice presentation. We'll go for the next paper, 881. Khalid Basham from I.I.T. Roorkee.
Yeah. Lateral capacity of skirted footing resting on level ground. Yeah, Khalid.
Yes, sir. Is my screen visible?
Yeah.
Yes, it is.
Chair, co-chair, and the organizing committee of Seismic Raje. Good evening, one and all present in the session. My name is Khalid Bashir. I'm working as a research scholar in the Department of Earthquake Engineering, I.I.T. Roorkee. Today, I will be presenting on the lateral capacity of skirted footing resting on the level ground. The main motive of my presentation is to understand the performance of skirted footing when subjected to lateral loads. And as this is a parametric study, we will be changing various parameters, and we'll try to understand with the help of feeder mechanisms how the skirted foundations will perform when subjected to lateral loads. So we usually come to the situation that shallow foundations aren't that adequate to cater heavy loads. And at that point of a time, what we usually do is either we need to improve the load carrying capacity of shallow foundations, or we need to search for some alternate strategies. In alternate strategies, we can go with different things. Either we can go with deep foundation, or we can reinforce the soil, or we can go with the skirted foundation. And in this presentation, I will be focusing more on the skirted foundation. So whenever we come to this site and where there's a poor bearing capacity, or we are having heavy structural loads coming from the top of this down to the substructure, so we have two options left. Either we need to reinforce the soil with various researchers have come with different things. Either we need to go with horizontal reinforcement, geosynthetics, geomembranes, and so many other techniques to stabilize. Either way, we can go with the deep foundations. But we usually see these techniques are, they are costing us immensely. They are not that economical. And even in some cases, that deep foundations become economical rather than improving the soil. So it is therefore suggested that we will go for some alternate approach, so that we can improve the bearing capacity of our traditional structures. What actually is skirted footing is that in normal footing, we will attach two skirts on the edge of the footing. That will actually increase the effective depth of foundation. That will the soil in between the skirts, that will act as a plug, so that the failure mechanism will not actually start from the base of the foundation, but it will actually start from the base of the tip of the skirts. From here, from the figures, we can see from in this figure A, this is a normal, we can say a stiff footing. And here in figure C, we are having a skirted foundation on which, on the edge of the stiff footing, we are having two skirts. And the soil in between these skirts is, it will act as a plug, because it will be intact to this skirts, and the feeder mechanism will start from the bottom of the skirts. There are various, this topic is not something new. On this topic, the research has been done from long. So we have researchers like Bransberg and Hov, we have Taney Cragg, we have Edatel. They have done, a good amount of research, and they suggest that, by using skirted foundations, we usually reduce the steel weight by half in installing a bucket foundation. They call it a bucket foundation or circular skirted foundation. It is same by calling it as a bucket foundation or a skirted foundation. So this is a circular skirted foundation or bucket foundation. It is installed by its own weight. It sinks usually in the marine conditions. How they install this, like they will, by its own weight, it will sink into the ground and find a suitable location, so that the loads are being transferred to the location. Why actually we do need skirted foundations? We usually find later loads coming from the earthquakes, from wind loads, water loads, or transmitting power cables. So we can't only go with the traditional footings. They will not be able to cater heavy loads or heavy lateral loads. So we will see how better, how effective is this skirted foundation to the lateral loads as well as the vertical loads. I'm not discussing the literature review, but yes, there are certain points, which I personally feel is very important for the listener session. In literature review, I found that majority of the studies are focusing more on the enhancement in the bearing capacity. Also, many researchers like Taney Cragg, Yun and Bransberg, E. Welp. So what they have found is that by increasing the effective depth of embedment due to the provision of skirts, that is less than the stiff footing. What they actually want to mean is that if we have a stiff footing and on the other end we are having a skirt foundation, and the depth of embedment is same, the skirted footing will be less effective than a stiff footing. But there is a contradictory statement made by the Al-Ghabari and Mohammad Azin and Park and Yo. They say that increase in the skirt length is more effective than the embedment depth of conventional stiff footing. So both these statements, they are contradictory to each other. On the other hand, Hisham, Hisham et al. And Professor Hisham, he says that if we compare skirted footing and block foundation at the same level, so they behave equally in similar conditions. So all these three statements, they are contradictory to each other. But yes, we should not forget Professor Bransberg, Taney, and Cragg. They have done tremendous, great work when we talk about skirted foundations especially for combined loadings. So there is no quantitative study, that actually sheds light on the improvement in lateral capacity of skirted foundation with respect to the strip. Here from the figures, we can see in traditional footing, the failure mechanism will start from the base of the footing, as we all know. But in the skirted footing, the failure mechanism, it will not actually start from the base of the footing, but it will start from the base of the skirts. So eventually it will increase the depth of footing, so thereby increasing the capacity. So the main objective of my research is that as we go on increasing the length of skirts, from the figure on the right hand side, we can see as we go on increasing the length of skirts, how the foundation will behave, not only for the vertical loads, but also for the lateral loads. And as a parametric studies, we will also we will vary the angle of internal friction, we have also changed the embedment ratio and the roughness between the skirt and soil, the roughness between the foundation and soil, but that is that is the extended part of this conference paper. So that is not being included in this presentation. We have used finite element limit analysis to carry out to determine the lateral capacity. Footing has been assumed to be resting on cohesionless soil. The domain has been selected large enough so that it will minimize the boundary effects. Since we are working on sand, so time scope will not have any much effect. We are taking the drain analysis and considering the Mohr column model. And in this conference paper, we are not taking care of the layered soil. That is the so it's an homogeneous soil domain, keeping 5. Foundation and skirts are modeled as rigid material, even though in the part we have modeled them flexible with hints and all, but more on rigid materials. The loads are applied for lateral capacity. We are first determining the bearing capacity. We will take a portion of the bearing capacity, put it on for the lateral capacity and increase the lateral forces to determine the lateral carrying capacity of foundation. Also in this analysis, we have used adaptive meshing technique. It will automatically take care of the fine and coarse meshes to decrease the computational time. These are the parameters which I'm so we'll be first having a look on the vertical loads and then combined loads. As we go on increasing the length of skirts, we can see from the figure that the more soil takes part in the shear dissipation. So when more soil takes part and the depth of this shear dissipation increases, so the bearing capacity goes on increasing. We can see here we are keeping the vertical loads and then checking the lateral capacity. The improvement factor for a length of skirt up to twice the width of foundation is up to 4 times that of the normal strip footing.
You have 1 minute.
And when we talk about the lateral capacity, so in figure A, the failure mode is by pure sliding. As we go on increasing the length of skirts and with for lateral capacity, the failure is more pronounced by the rotation. In figure B, C, and D, we can see the failure here in A is by mere shearing, sliding, and for rest of the figures, as we go on increasing the length of skirts, the failure is more by rotation. So these are the improvement factors. As we go on increasing the length of skirt, the improvement will obviously the improvement factor, which is a ratio between the bearing capacity of skirted footing and by unskirted footing. So we can see when we are having the length of skirt as twice width of foundation, the improvement factor is 11 times that of a normal strip footing. And in a lateral capacity on the right hand side, we can see it's up to 15 times. I'm just moving fast. So this is the validation. As we go on increasing the phi, the bearing capacity will increase. As we go on increasing the length of skirts, the bearing capacity and lateral capacity both will increase. This is the percentage increase. We can see for phi as per I.I.Sc classification for very loose to medium dense sand up to 35. This skirted footing is more getting better results, and we are recommending for this portion of soil up to medium dense and for length of skirts up to 1. As we increase the
Khalid, you have time up. Okay, you can conclude.
Okay, this last slide. 10 more seconds, please. So when we compare this is validation with the Professor Taney and Craig. What they say is that skirted foundation and stiff foundation will behave equally in bearing capacity. And yes, in our case also it's behaving equally. But when we talk about the later loads, it's not behaving equally. Skirted foundation is not behaving as that of stiff footing. That can be, in our opinion, it's because of the rotation taking care of. These are my references. Thanking you.
Yeah, thank you. Participants, if you have any queries, you please ask to the presenter. You can.
I think there are no questions. Thank you, Khalid.
Sir.
Unfortunately, my internet connection was disrupted during your presentation. So really, I don't know. And your paper is also not available yet to us. So obviously, I don't have anything to ask. Professor Chandra, I think you can continue. As a ending note, I thank Professor Cox and for his state-of-the-art lecture. Really, it was insightful and also has got a new avenue for geotechnical, particularly ground response analysis research field has got a new avenue and also new hopes for one-dimension analysis. And all the 5 presenters, I wholeheartedly thank for their presentation and also active participation of the participants in for the interaction, all their interaction. With this ending note, I request my co-chair to sum up the session with his remarks. Thank you, Chandra. Thank you, Govindraju. And all the organizers, including Professor TGS, Professor Jetka, Dinesh, Patsati, Govindraju. Really, your efforts are really seen. Yeah. Thank you, one and all. Over to Professor Chandra.
Thank you for the opportunity, sir. I'm especially thankful to the our my co-chair and especially Govindra sir and Srivachala sir and all these presenters. Even we are also enjoyed all the sessions, and it's really new topics. Each one is considered a new one. And thank you so much for giving this opportunity, sir, especially. Now, Govindra sir, what we can
I
do
will
here?
take. I will take over. Yeah.
Okay, thank you so much.
Now it is my floor now.
Yes, sir.
In fact, we overshooted by 15 minutes, so that no issue, because we had very fruitful discussion in all of these papers, and it is a basic requirement. So that sometimes you have to be flexible also. So here I would like to thank the chair of this parallel technical session, Dr. K.V. Vijayendra, to accept our invitation, make himself available in spite of his busy schedule to chair this technical session. Sir, on behalf of the organizing committee and on my behalf, I thank you very much for your presence and giving critical remarks in each of the presentation. I also thank the co-chair, Dr. Chandra Bogireddy, was actively involved in raising the critical comments and then conducting the questionnaire session. On behalf of the organizing committee and on my personal behalf, I thank profusely Dr. Chandra Bogi Reddy for his valuable time and chairing the session also. At the same time, I would like to take a note of Professor Brady Cox for delivering a state-of-the-art practice lecture wonderfully and giving a highly informative lecture in this particular session. Sir, I thank you very much on behalf of the organizing committee. I also thank the authors of the today's presenters, Sukant Das, Rajeshwari JS, Suvendu Kumar, Das NK, and Khalid Bashir for delivering very interesting information out of your research contributions. I thank you one and all.